All right, now we'll be doing chapter 13.2 again today. That is a root mean square speed. Now, before we look at root mean square speed, what does it mean by root mean square speed? Let us begin from the mean speed. Okay, so mean speed means it's average speed. So this is the symbol. Okay, so this is a symbol for mean speed. Now, for example, if you have 5 particles, they are all moving with different velocity. Okay, then basically you just add up, okay, add all velocity together and then divide by 5. Then that is your mean velocity. Okay, so this is what we call mean speed. Okay, mean speed, to be more precise, because we're not looking at directions yet. And then mean square speed means that now you square the velocity. Okay, and then you calculate the mean values of it. So this is what we call mean square speed. Now, what does it mean by root mean square speed? Root mean square speed means that now that you have this mean square speed, so you square root it. Okay, you square root this value, and now this is what we call root mean square speed. Okay, and this is our VRMS. Okay, this is our VRMS. So root mean square speed basically is equal to the square root of the mean square speed. So you have to know all these terms because they all carry different meaning. And that is what you're going to do in your exercise 2 questions 1. Okay, now before we look at the questions, okay, as I told you in the lecture, there are 7 assumptions that you need to know, you need to memorize. Okay, the first one is that all gases, they are made up of identical atoms or molecules. So if you're looking at the same types of gas, for example, oxygen, we assume all of the atoms, all of the molecules, they are the same. Same in terms of what? In terms of the shape, in terms of the mass, and so on. Okay, that is the meaning of identical. So you assume they are all looks alike. They all have the same characteristic. Okay, and then all atoms and molecules, they move randomly. Okay, they move randomly means that they have no fixed direction. So you cannot predict where are they going to move. And then the volumes of these atoms and the molecule is negligible when compared to the volumes of the container. Okay, when compared to the volume occupied by the gas. So for example, in this classroom is that big. If you're just looking at the molecule of one oxygen, does the volumes of the oxygens matter compared to this class? Obviously no, it's negligible. You can't even see it, you can't even feel it. Okay, so that is the meaning of the third assumption. The volumes of the atoms or molecules is negligible when compared to the place that is being occupied by the gas. And then the intermolecular forces are negligible except during collisions. Okay, but when we look at the intermolecular forces are negligible, it means you can actually neglect its potential energy. Okay, because of this 4th assumption, we assume the potential energy is negligible. Right? It's not equal to 0, but it's negligible. It won't affect the motions. It won't give Earth any other effect. And then the interatomic or molecular collisions, they are always elastic. Now, why is it important to say that they are elastic? Because we assume there's no energy loss. Okay, if it is inelastic, then that means it comes with energy loss. So now our assumption, we assume it is an elastic collision. So the durations of a collision is negligible compared to the times travel of the atoms. And then the last one is that the atoms and molecules, we assume they always move with the same or constant velocity between collisions. Okay, so gravity has no effect. That is the last assumption. So these 7 assumptions, you need to memorize it and you need to understand what does it mean. And then based on these 7 assumptions, they then derive a set of equations that can be used to calculate VRMS. Okay, where first one, we have VRMS equals to square root 3kT over small letter m. This is the first equation. And at the same time, VRMS is also equals to 3 RP over capital letter M. Okay, and one last equation based on the derivation. it is equals to square root 3 pressure divided by the density rho. Okay, rho. So this is the density, right? This symbol, it represents density. So what is the equation for density? Density is equals to V over M. Okay, V over M. So that is the equations, right? That is the equations that we're going to use in the calculations. All right, now let us go back to the equations again. Okay, the things that we want to look at right now is the meanings of the symbol in our equations. Okay, the meanings of every symbol in the equations. Okay, yeah, let me see. Oh, equation terbalik. It should be M over V, sorry. Okay, it should be M over V. Okay, now let us look at these two equations. Our main focus would be these two equations. Okay, our main focus would be these two equations. So 3kT over M and 3RT over M. One with small letter m and one with capital letter M. This capital letter M, it just carries the meanings of molar mass. So it's very simple. Okay, it's very simple because molar mass depends on the type of the gases that you're looking at. If you're looking at, for example, the hydrogen gas, then the molar mass is 2 grams per mole. Just make sure it should be in SI unit. Okay, it should be in SI unit. So what is the SI unit? Kg mole negative 1. Okay, now the things that I want you to be careful is what? Is the small letter m. Now, small letter m, we know it means a mass. Okay, the mass in kg. But the mass of what? The mass of all of the gases, the total mass, or the mass of a single particles. So this m, it actually refers to the mass of one molecule. Okay, one molecule. So you need to find out what is the mass of one molecule first before you apply these equations. You cannot simply put in the total mass. If you use total mass in these equations, then you wouldn't be able to obtain the value needed. All right. So it should be the mass for just one molecule. So sometimes questions will tell you, now you have 10 kg of oxygen. 10 kg is not the mass that you're going to use in this equation. You need to find out in that 10 kg, how many molecules do you have? Okay, and then you divide it by the amount of molecule in order to obtain the mass of one molecule. For example, now it tells you, okay, let's say 100 gram. 100 grams of O2 contains, let's say, this is just an example. Okay, 100 grams O2 contains 1,000 molecules. Then you need to find out every single molecule, okay, is equivalent to how many grams. Right? So 100 grams is 1,000 molecule. One molecule is how many grams? Habis tiba-tiba stop. 0.1 gram lah, guys. Okay? So you find out what is the value of the mass for just one molecule. You don't look at the total mass in the container. Most of the time, questions will give you total mass. You yourself have to find out what is the mass of one single molecule. All right? So now let us look at the questions. So questions 1, I'm not going to show you how to do it. I give you 2 minutes to solve questions 1. It's just very simple. Why? First one is just asking for the mean speed. Okay, the first one. And then you have the mean square speed. I told you already how to calculate it. And then after you obtain the mean square speed, you square root it. That is the answer for question C. So now I give you 2 minutes to solve it before we look at questions number 2. All right? try questions 1. Just very simple questions. All right, so now let's look at questions number 2. Questions number 2, a cylinder of volume 0.08 meter cube contains oxygen gas at the temperature of 280 Kelvin and pressure of 90 kilopascal. So as usual, okay, we are going to write down the information first. Okay, let us write down the information first. So questions number 2. Okay, questions number 2, the information given is volume. So V equals to 0.08 meter cube. Yes, we have it in SI unit. Very good. And then temperature T is equals to 280 Kelvin. Again, it is in SI unit, so you don't have to do anything for it. And then given pressure equals to 90 kilopascal. So make sure to change it into times 10 to the power of 3. Right? So P equals to 90 times 10 to the power of 3 Pascal. So given R equals to 8.31 is a constant value, and then Boltzmann constant K equals to 1.38 times 10 to the power of negative 23. Molar mass, okay, let me write down molar mass, because molar mass is based on questions. Okay, so I'm going to write down the value given based on the questions given. So molar mass is equals to 32 gram per mole. Aha. If you look at this value, again, it's not in SI unit, right? So you yourself have to change it into SI unit first. So it is equals to 32 times 10 to the power of negative 3 kg mole negative 1. So that is how you do the unit conversions. And then the last one, number of Avogadro, again, that is just a constant value. For constant value, I'm not going to write it down because you'll be given a list of constant variables, constant value. You just have to look at the list, all right? So all this information, they are all based on the questions. Different questions, they have different values. So I write it down as information for this question. Now, let's look at questions A. Questions A asks you to determine the mass. How are you going to determine the mass in a cylinder? So if you look at these questions and if you look at the information given, according to the information given, now you have V, you have T, you have P, okay, and then you have a molar mass. Well, I think we don't have any equations that contain these 4 variables, right? But what we do have, well, you have V, T, and P, and now you are looking at the same type of the gas, so you can apply ideal gas law, where PV equals to nRT. My next question would be, how am I going to relate these equations to molar mass? What is the things that I can do to link these information, okay, to change, to modify this equation so that it can be used with the molar mass? N equals to M over M. Good. So now I'm going to expand the equation. So I have PV is now equals to, okay, equals to what? Equals to small letter m divided by molar mass, RT, right? So now that I have all the information needed, I should be able to determine the mass of the gas in the cylinder. And this mass is the total mass, right? So the mass that we use together with the numbers of mole is the total mass. Whereas the mass that we use in the equation for VRMS is the mass for just one molecule. So make sure you don't get confused between different M in the same sum topic. Right? Dalam same topik yang sama, kamu memang ada M dalam berbagai jenis equations, tapi ada equations merujuk kepada total mass, ada equations merujuk kepada mass for just one molecule. So buat catatan dalam buku Anda, dalam nota Anda supaya Anda tak keliru. So this one is the total mass. So if you plug everything into the equations, all these values into the equations, you should obtain M equals to 9.9 times 10 to the power of negative 2 kg. Good. Okay, 10 to the power of negative 2 kg. So that is the answer for questions A. So questions B asks you to determine the numbers of oxygen molecule in the cylinder. So you want to determine the numbers of a molecule, which means the question is asking for capital letter N. Okay, it's asking for capital letter N. So the equation that can be used now, you have small letter m, you have capital letter N. And you know numbers of Avogadro is a constant value. Therefore, we can use this relationship. N equals to m over n equals to n over NA. So we are going to crop this part out and use it for our questions B. Okay, so you plug in the value, you got the mass from questions A, and then molar mass from the main questions. Number of Avogadro is a constant value, so N is equals to 1.86 times 10 to the power of 24. Okay, now you need to write down the unit. Since this question is talking about molecules, therefore the unit is molecule. Okay, you cannot leave it blank. N is a quantity. Every quantity must come with unit. Sometimes questions might ask you to calculate the numbers of proton. Then the unit would be proton. If question asks you to calculate the numbers of electron, then this value, this unit should be written as electron. And this question asks you to calculate the numbers of oxygen molecule. You are looking at molecules, therefore you write it as molecule. If question is asking for atoms, then here should be atoms. Okay, don't leave it blank. And it does have a unit. Okay, dia ada unit, so Anda kena berhati-hati dengan N. So this is a very common same misconception in these questions, okay, in this topic. Okay, so now that I have done with questions A, questions B, and how about question C? Question C asks you to calculate the root mean square speed, okay, VRMS. So very simple. You have molar mass. Straight away, you should be able to calculate the root mean square speed, okay, where VRMS is equals to square root 3RT over capital letter M. Okay, so this is how you solve it. Since you are given molar mass, this is the easiest way. But as an exercise, what I want you to do, other than this equation, I want you to apply VRMS equals to square root 3 KT over small letter n as well. Method 1, method 2. I want you to show both methods in your books. Try to think how are you going to apply this equation. When this n, it should be the mass for one molecule. Okay, one molecule. So if you look at questions A and questions B, questions A tells you M is equals to 9.9 times 10 to the power of negative 2 kg. This mass is not for one molecule. This mass is for 1.86 times 10 to the power of 24 molecule. So now that you know the mass for 1.86 times 10 to the power of 24 molecule, try to think, how are you going to determine the mass for just one molecule? Okay, macam mana kamu nak kira mass untuk satu molecule? So now I give you 5 minutes to complete these questions because I want you to try these last questions by yourself. Okay, learn how to use both equations. show what is the difference between these two equations in your books. Okay, you yourself should write out a bit of notes. Okay, that tells you how to use these two equations. So sendiri buat catatan dalam buku Anda, macam mana menggunakan kedua-dua equations dia. Okay, apakah nilai yang sepatutnya Anda guna? Tunjuk dengan jelas step by step di dalam buku Anda. So you should get same answer, okay? You should get same answer. It doesn't matter whether you're using 3RT or 3KT. How did we calculate the mass for one molecule? Based on the answer from questions A and questions B. Besok semua tak tahu macam mana nak kira mass for one molecule. Okay, now we know 9.9 times 10 to the power of negative 2 kg is the mass for 1.86 times 10 to the power of 24 molecule. Alright, so this is the information that we have right now. What we want to do is that now we don't know what is the mass in kg for what? For just one molecule. So this is the relationship. Now that you have these two relationships, what you can do is you use left-hand side divided by left-hand side, which is an unknown. You can write it as x, for example. Okay, you can write it as x. And then right-hand side divided by right-hand side. Okay, kiri bahagi kiri sama dengan kanan bahagi kanan. Then from there you should be able to determine the values of x. Right? That is how you find out what is the mass for just one molecule. Okay, so if you're done, then look at questions number 3. So questions number 3 is just a very simple questions. Okay, questions number 3. Questions number 3, the root mean square speed of an oxygen molecule in a container of oxygen gas is 625 meter per second. So you're given VRMS. Okay, so as usual, write down the information first. So VRMS given 625 ms negative 1. What is the temperature of the gas given the molar mass of oxygen? So again, you're given molar mass equals to 32 gram per mole. Once again, you're given the unit in terms of gram. So convert it into kg. So 32 times 10 to the power of negative 3 kg mole negative 1. Right? And then questions asking for P. So if you look at the information given, okay, then straight away you should know which equations to use. So since you are given about, okay, you are given the RMS value, and then you are given capital letter M. If you remember this, I told you in the previous class, in the lecture, if you have molar mass, the capital letter M, then the best partner would be R. Okay, the best partner for capital letter M, molar mass, and also for the mole, numbers of moles, small letter n, their best partner is R. Whereas if you are given the mass in terms of kg, or if you are given the numbers of molecule, then the best partner would be Boltzmann constant K. Right? So you need to know which equations to use. So you have capital letter M, then obviously these questions can be solved by using VRMS equals to square root 3 RT over capital letter M. Okay, so their partner, the partner for capital letter M is always R. Okay, it's always R. So that is how you solve question number 3. Just plug in the value and then rearrange the equations. And then questions number 4, I want you to try it as well. Okay, so I give you, now it's 39, I give you 5 minutes to solve both questions 3 and 4. Questions 4, same as questions 3. Okay, the only difference is that now you are given temperature in degrees C. So you need to change it into SI unit, which is Kelvin. Right? So questions 3 and 4, I give you 5 minutes to solve both questions. Then we will proceed to last subtopic 13.3 internal energy. Okay, 5 menit untuk Anda siapkan kedua-dua soalan, and then kita akan bergerak ke subtopik yang terakhir, internal energy. If you have any questions, you may ask. Online punya kalau ada masalah anda boleh buka mic tanya atau anda boleh type dalam chat box. Okey, kalau takut saya terlepas dengar. Anda catat dua equations ini. Okay, dua equations ini tercicir di dalam waktu kita bincang kuliah sebelum ini. Alright. So right now these two equations. So page 158. Okay, or for those who use a printed note yang print sendiri punya, I think it should be on the page 294. Okay, yang sendiri print punya nota. Kalau beli buku punya, page 158. So these two equations, all right? So these two equations, it also came from a derivation. And once again, I'm not going to show you how to derive it. So what you have to do, you just need to write it down and then apply it. Okay, apply the equations. So if you look at the first equations, PV equals to 1/3 and M mean square V. Okay, mean square V. Now this whole thing at the same time it is also equals to NKT and also nRT based on the things that you learned in 13.1 ideal gas law. All right. So this one at the same time is also equals to NKT and it is also equals to nRT. All right. So they are interchangeable. Depends on how you apply the equations. Right? Sometimes if you don't have enough information to calculate NKT, then you can straight away use PV. So 1/3 NM mean square V, okay, equals to PV, and it is also equals to NKT, it is also equals to nRT. That is the meaning. Alright, semua ada nilai yang sama. So Anda sebenarnya boleh tulis dia dalam satu baris. Okay, for that four equation. So kalau kamu tak boleh guna equations, PV sama dengan 1/3 NMV square, Anda actually boleh guna 1/3 NMV square sama dengan nRT. Dalam pengiraan, tak ada masalah, nothing's wrong, okay? Because they are all equal. Alright, so these equations, you just have to know how to apply it. So this one is for pressure. Pressure is equals to 1/3 rho and then mean square speed. Okay, mean square speed. So you can try to solve exercise 3 by using these equations. So let us go through exercise 3 quickly. Okay, let's go through exercise 3 quickly. And then we will take a short break before we proceed to exercise 4. So exercise 3, the density of oxygen gas. So you're given density where it is equals to. Okay, so exercise 3, questions 1. Given rho is equals to 1.43 kgm-3, okay, the mass per unit volume. Estimate the root mean square speed of oxygen gas molecule at STP. So given standard pressure, so standard pressure in this question, they give you the value P is equals to 101 times 10 to the power of 3 Pascal. So question asking for root mean square speed. But if you look at the equations over there, the equations that we have is P is equals to 1/3 rho and then mean square speed. By using these equations, the values that you will obtain is mean square speed. Okay, mean square speed. It is equals to 2.12 times 10 to the power of 5 m squared as -2. That is the values that you will obtain by applying this equation. But according to the questions asking for root mean square speed. So you need to know the relationship between VRMS with this value. So according to the definitions of VRMS, root mean square speed, VRMS is actually equals to square root mean square speed. So you need to square root this value. So the final answer should be 460.43 ms -1. Okay, 460.43 ms -1. So that is how you calculate root mean square speed. So based on the information given, the only values that you can calculate is mean square speed. So VRMS, you need to square root the value. All right, you need to square root the value. So that is questions 1 for you. Okay, that is questions 1. So you try and see whether you can get an answer or not. Okay, now let's look at question 2. Question 2, it gives you a 0.2 kg helium. So main questions give you M equals to 0.2 kg. It's contained in a container at 150 kilopascal. So pressure is equals to 150 times 10 to the power of 3 Pascal. VRMS given. Okay, now you have to be careful with the values given. If you look at the questions, now you're given a value 2.45 km per second. So km is not SI unit. So what you need to do, okay, you need to change it into SI unit. Therefore, VRMS is equals to 2.45 times 10 to the power of 3 ms negative 1. Okay, so that is your VRMS. Questions A asks you to determine the volume of the gas. Well, the volume of the gas, if you look at the questions, okay, if you want to apply equations PV equals to 1 over 3 NMV squared, seems like we don't have enough information, right? So the equations that we can use right here is P, okay, questions A, is P is equals to 1 over 3 rho V squared. Okay, 1 over 3 rho V squared. So this is the equations that we're going to use. Now, by looking at these equations, P equals to 1 over 3 rho V squared. Question asks us to calculate volume, right? We don't have volume in these equations. But if you look at these equations, we have a term known as density. And we know density is equal to M over V. Therefore, these equations can then be written as P equals to 1 over 3 M over V. Okay, M over V, and then V squared. Aha! One more question. I don't have V squared right here, right? But then, if you look at the questions carefully, I have the values for VRMS. And we know the relationship between VRMS and V squared is that VRMS is equal to square root V squared. Rearrange the equation. Mean square speed is then equals to VRMS squared. So this equation, okay, you can then rewrite it again as P equals to 1 over 3 M over V and then VRMS squared. So this is the equations that we're going to use in questions A. Okay, so you try to apply these equations, then you should obtain V equals to 2.67. Okay, so V equals to 2.67 ms negative 1. So you tried it. And then questions B, basically just a very simple questions. Okay, you just apply ideal gas law. So you try to solve it by yourself, questions B. Okay, kamu coba jawab soalan B sendiri. So itu basically kita dapat banyak kali dah soalan B. Guna ideal gas law saja, because we want to determine the temperature. So you have volume, you have pressure, you want to determine the temperature, you apply ideal gas law. Okay, so questions B, I leave it to you. And now it's 2:55. So we are going to take a short break. Okay, we're going to take a 5 minutes break. We'll continue again at 3 p.m. Okay, kamu coba siapkan ini, and then nak tandas ke, nak pergi minum air ke, pergi, kita sambung balik pada jam 3. Okay, pada jam 3. Yep. Any questions? Okay, rasanya kebanyakan pelajar dapat soalan B 963.09. Rasanya itu yang betul, okay? Answer dalam buku Anda macam salah. Right, macam salah. Okay, now let's see. Okay, so now let's look at 13.3. So 13.3, they are all about monoatomic, diatomic, and polyatomic. These three things. Okay, they are all about these three things. So let's see what is the main difference between these three things, and I will do a bit of corrections of the tables in your books. Okay, so in your books, you are given a table on the last page of this chapter. So actually, for me, the table is a bit incomplete. Okay, but that one we'll leave it first. Now let's see what is monoatomic. So monoatomic means that it just has one atom. Alright, so this is your monoatomic. So diatomic, we have two. Okay, two of them, they're joining by a bond. And sometimes diatomic, okay, for this example, sometimes you'll consider the linear polyatomic as well. Okay, where you have three atoms, they are joining in a straight line. But that one seldom happens. And I think so far I've never seen that type of questions in your syllabus yet. Right, so you have two types, either linear polyatomics or a diatomic. So polyatomic in this case, it means three atoms or more, okay, they form at an angle. So the angle is not equals to 180 degrees, okay, there's an angle in between the atoms. So this is our polyatomic. Okay, so now let's see. The first things when it comes to this chapter is that we need to learn how to determine the numbers of degree of freedom. Okay, the numbers of degree of freedoms of these three types of molecules, okay, your atomic. So the first things that you need to know is about the translational motion. So there are two types of motions that we're going to look at. The first one is what we call translational motion. Okay, translational motion. And then we have another one is what we call rotational motion. Right? So for translational and rotational motion, what is the difference between them? So for example, now you have one atom. Okay, you have one atom. So this is an atom. This atom, if it moves along, okay, now I'm going to form three axes first. Okay, I'm going to call this, okay, the black color one is the x-axis, the blue color one is the y-axis, and then the red color one is the z-axis. All right, so it forms a three axis like this. So, well, this one is horizontal, vertical, and now this one, when it comes to z-axis, now we know x-axis is horizontal axis, y-axis is vertical axis. Then what is the directions of z? The terms that we use to describe z is either out of the page or into the page. So how to tell whether it is out of the page or into the page? Into the page means if you look at the object is moving towards the paper, towards the whiteboard. It is going into the whiteboard. So that one we say into the page. If it is coming out from whiteboard and moving towards you, then that one we call it out of the page. Right? So first example, monoatomic. When it comes to translational motion, now what does it mean by translational motion? It means linear motion. So now let's say this is your monoatomic. Okay, just one atom. If it moves along x-axis, can you see it? Well, can, right? So you can see it move, obviously. You can see it move along y-axis, obviously. And then again, you can see it move along z-axis, right? So in that case, because we can see the motions clearly along three different axes, okay, then we can say it has 3 degrees of freedom of translational motion. The energy can be stored or can be used along these 3 motions, okay, because it happens obviously, right? It happens and you can see it happens obviously. So in that case, we say it has 3 degrees of freedom of translational motion. Okay, 3 degrees of freedom. Then how about diatomic? Okay, so let's say now I have a diatomic like this. Okay, so imagine this is diatomic. All right, you have 2 atoms attached at the both ends. So now this is diatomic. Can diatomic move along x-axis? We can. Can it move along y-axis? Yes, it can. Can it move along z-axis? Oh, yes, it can. In that case, when it comes to diatomic, we also say it has 3 degrees of freedom. Okay, the energy can be stored or can be used in 3 different ways. So 3 degrees of freedom, right? And then when it comes to polyatomic, okay, so this is our polyatomic right now. There's an angles between them. So again, this polyatomic, it can move along horizontal axis, it can move along vertical axis, it can move along z-axis, okay? In which, again, when it comes to polyatomic, okay, it also contains 3 degrees of freedom of translational motion. Okay, so 3 degrees of freedom. So this value, okay, these are translational motions. We use it to calculate translational kinetic energy, which is our KTR. Okay, we'll look at it after this. Okay, now how about rotational motion? Okay, how about rotational motion? Now we know an atom is something very, very, very small, right? So if it rotates, if you take this x-axis as the axis of rotation and it rotates around the x-axis, can you see it? No, not really, because it's just something very small. So try to imagine, now this is your x-y axis. Okay, your y-axis, your x-axis. This is the atom. So now it rotates around the x-axis. It uses the x-axis as the axis of rotation. Okay, sebagai garis tengah untuk dia berpusing. Axis of rotation, you guys know the meaning, right? So if it uses x-axis as the axis of rotation and it rotates around the x-axis, you can't really see anything. Okay, why? Because the radius is too small and we can say it's negligible. So in that case, we say it has no degree of freedom. Okay, it has no degree of freedom because it's too small. Okay, it's too small and can be neglected. Boleh diabaikan, right? Boleh diabaikan. So in this case, okay, in this case, we can say it has a negligible energy when it comes to rotational motion. Sebab R dia terlalu kecil. So it doesn't matter whether it rotates around the x-axis, around the y-axis, or around the z-axis, because you just have one very small atom, and the radius is very small. In this case, we say it is negligible in all three directions. Therefore, when it comes to monoatomic, right, we say it has 0 degree of freedom of a rotational motion. All right, so it cannot possess energy in a rotational motion. Why? Because the radius is way too small. It is negligible. Okay, it is negligible. Boleh diabaikan. Now, when it comes to diatomic, okay, so when it comes to diatomic, then what happens? Okay. Yeah, where's my calculator? Okay. So when it comes to diatomic, now this is diatomic, okay? This is diatomic. Again, I have 3 axes. This diatomic, now let's say is initially it looks like this, okay? You place it like this. If it rotates around y-axis, can you see it? Yes, it's quite obvious, right? The radius is quite large, okay? It's quite big from the axis of rotation, okay, which is your y-axis. So if it rotates around z-axis, can you see it? Yes, okay, initially you place it like this, okay, at the center, at the origin. So if it rotates around the y-axis, you can see it. If it rotates around the z-axis, you can also see it. But if it rotates, if it takes x-axis as the axis of rotation and now it's rotating, can you see it? No, it's not obvious. Once again, the radius is very small because it rotates like this. Okay, so apa yang kita buat? Okay, initially dia di origin. Okay, so sekarang apa yang saya nak buat? Saya abaikan 2 axis yang lain dulu. Okay, I'm going to ignore the other 2 axes. So this is how you place it. This is your y-axis. Now it takes y-axis as the axis of rotation, so they rotate. So you can see it. Okay, now you keep it. You put it like this. You still put it like this. Now you rotate it around z-axis. If you rotate it around z-axis, you can also see it, right? The radius is very large. But now if you place it like this, and this is your x-axis, okay, so now it uses x-axis as the axis of rotation, it rotates like this. So obviously, when it rotates around the x-axis, it can be neglected again. Why? Because the radius is very small from the axis of rotation, and thus the motion can be neglected. Right? The motions can be neglected. So when it comes to diatomic, that's why we say the degree of freedom of rotational motion is just 2 degrees of freedom. Okay, 2 degrees of freedom. Why? Because you can neglect one of it. Okay, yang parallel to your diatomic. Okay, pasti yang parallel dengan kamu punya diatomic, kamu boleh abaikan sebab bila dia rotate, okay, dia punya efek tak besar. Sebab apa? Sebab radius of the atom is very small. So if it rotates around the x-axis, then the energy can actually be neglected. Right? Okay, so now how about polyatomic? Okay, how about polyatomic? So now this is my polyatomic. Okay, so again, I'm going to look at that axis by axis. So initially, I place my polyatomic like this. So this is my y-axis. So if it rotates around y-axis, can you see? Yes, it's quite obvious, right? Now, if this is my z-axis, now if it rotates around z-axis, yes, it's quite obvious as well, right? So now, again, if this is my x-axis, when it rotates, can you see? Yes, so it's quite obvious in all 3 directions, in all 3 axes. Therefore, when it comes to polyatomic, we say it has 3 degrees of freedom of a rotational motion. Okay, because it can possess energy in all 3 axes. It doesn't matter what is the direction of its rotation. Dia boleh dapat energy, dia boleh guna energy atau store energy in all 3 axes. right? So that's why we have 0 to 3 when it comes to rotational motion. That is the reasons why. And of course, in reality, there's one more motion called vibrational motion. But that is no longer in our syllabus. Vibrational motion, it happens when your atoms, they are being placed in a very high temperature and they start to vibrate. Okay, so that one is a vibrational motion. When it vibrates, it has 2 degrees of freedom. Right, but that one is not in your syllabus. Okay, I just tell you as an additional information. So in our syllabus, we just have to know how to count the degree of freedoms in the translational motions and how to count the degree of freedoms in rotational motions. Why? Because translational motion, we use it to calculate translational kinetic energy. Okay? Whereas rotational motion, we use it to calculate rotational kinetic energy. Okay, rotational kinetic energy. So there are 2 different types of energy. And when you combine these 2 degrees of freedoms together, okay, so the books will just call it total degree of freedom. Okay, your degree of freedom. So the total degree of freedom for monoatomic is 3. The total degree of freedom for diatomic is 5. The total degree of freedom for polyatomic is 6. So we use this information to calculate the so-called average kinetic energy. Okay, your K average. Okay, your K average. Average kinetic energy. So the questions will tell you which one to calculate. Okay, if questions mentions translational kinetic energy, then you use the first one, the degree of freedom for translational motion. If question asks you to calculate rotational kinetic energy, then you use degree of freedom for rotational motion. But if the question asks you to calculate total average kinetic energy, then you use the total degree of freedom for 2 types of motion. Okay, from both of them. Okay, so next, how are we going to calculate the energy then? Now we know how to determine the degree of freedom. Next, we want to see how are we going to calculate the kinetic energy. So there are 2 types of kinetic energy that can be calculated. So first of all, let's look at the principle of equal partitions of energy. In this subtopic, there's a new principle that you need to know, okay, which is known as principle of equal partitions of energy. Now it tells you the average kinetic energy stored in every single 1 degree of freedom is equals to half kT. Okay, so for every 1 degree of freedom, it consists of energy equivalent to half kT. Okay, half kT. So if question, for example, now if question asks you to calculate the energy in a translational motion, the translational kinetic energy for 1 monoatomic. So 1 monoatomic, it has 3 degrees of freedom. So in that case, the total translational kinetic energy in monoatomic is, if 1 degree of freedom is half kT. Now questions ask you to calculate translational kinetic energy for a monoatomic. So what is the translational kinetic energy? 3/2 kT. Very good. Okay, 3/2 kT. If you're looking at 1 molecule. Okay, if you're looking at 1 molecule. So once again, if you're looking at 1 molecule, okay, yeah, 1 molecule. So if you're looking at 1 molecule, okay, so 1 molecule, it has 3 degrees of freedom of translational motion. So if you want to calculate its translational kinetic energy, KTR, then it is just equals to 3 times 1/2 kT. Why? Because it has 3 degrees of freedom of translational motion. So in this case, when it comes to 1 molecule, okay, for 1 molecule, the translational kinetic energy is 3/2 kT, right? And then how about its R? KR, rotational kinetic energy. Well, it has 0 degree of freedom, right? So in that case, the rotational kinetic energy is just equal to 0. And then how about its average kinetic energy? So average kinetic energy, we look at the total. Okay, we look at the total. So you can either add them up, or you can either look at the total degree of freedom. So for monoatomic, the total degree of freedom is 3. Therefore, once again, this is 3 times 1/2 kT. Okay, so when you have a case for one molecule, basically the equation is K is equals to F/2 kT. This is for one molecule. So you look at whether you're looking at the R, you're looking at the R, or you're looking at the average. And then you try to identify the numbers of degree of freedom. Now, if you have a more than one molecule, for example, now you have n amounts of molecules. Okay, you have n amounts of molecules. Then how are you going to calculate KER, for example, for polyatomic? Okay, so this is an example for monoatomic. So now for n molecule, now I'm going to take diatomic would be better. Okay, I'm going to take diatomic as example. Okay, I'm going to take diatomic as example. So if I have diatomic, how am I going to calculate the KTR? So KTR for one molecule, okay, for one diatomic, it is equal to 3 times 1/2 kT. This is for one molecule. Now you have n molecule. So what are you going to do? Times n. Right? So this is the value for one molecule. When you have more than one, then you just times n. So therefore, the total translational kinetic energy would be 3/2 nKT. Okay, 3/2 nKT. Now, if you look at the rotational kinetic energy for a diatomic, for one diatomic, then it would be 2 times 1/2 kT, because it has 2 degrees of freedom in a rotational motion. So for one diatomic, it is equal to 2 times 1/2 kT. If you have more than one, if you have n molecules, then you just times with n. Okay, then it is equals to 2/2 nKT. Right, 2/2 nKT. This is the rotational kinetic energy, just rotational. How about average kinetic energy? Well, average kinetic energy for one molecule, it has 5 degrees of freedom. So 5 times 1/2 kT. But now you have more than one molecule. You have n amounts of molecules. So you times with another n. Then it is equals to 5/2 nKT. So for more than one molecule, the general equation is K equals to F/2 nKT. Okay? So K is equals to F/2 nKT. So basically, this is the equation that we use in all of our calculations. Why? Because if you're given an example with just one molecule, then you just replace n with 1. Okay? So ini kita panggil general equation. Okay, general equation. So general equation ini kita pakai kalau kamu ada case yang ada satu molekul saja, kamu gantikan n dengan 1. Right? So yang saya tunjuk semua ini, saya tunjuk Anda macam mana derive sampai dapat general equation. Kenapa kita dapat ini sebagai general equations kita? Right? So dia ada sebab dia. Starting from degree of freedom, and then the meanings of principle of equal partitions of energy, which tells you 1 degree of freedom contains half kT of energy. So from there, we then calculate the translational kinetic energy, rotational kinetic energy, and the total average kinetic energy. Okay? And then from just one molecule, we then proceed to a more complicated cases where we have more than one molecule. Okay? So we have n amounts of molecules. So in 13.3, this average kinetic energy at the same time it is equal to your internal energy. Okay, it is equal to your internal energy, which is U. Why? Because according to definition, internal energy U, which is equals to KE, kinetic energy, plus PE, potential energy. And we assume potential energy is equal to 0 because we say intermolecular force can be neglected in the assumption. So we assume this is equal to 0 because we assume no intermolecular force. Therefore, we say internal energy is also equal to kinetic energy. Right? It's also equal to kinetic energy. So dia ada sebab-sebab kenapa kita dapat equation begini, kenapa kita dapat nilai begini. Right? So this whole thing is slightly more complicated. I give you 5 minutes to complete the table. Okay, to complete the table. So you start from this table with the header, monoatomic, diatomic, polyatomic. And then you write down the diagram, the numbers of degree of freedom in translational motions, rotational motions, and the total. And after that, followed by the energy for one molecule, and then followed by the energy for n molecule. Okay, so basically apa yang saya nak kamu buat, can I write it? Okay, so this is a table. Okay, this is a table. So you have a monoatomic, diatomic, polyatomic. You start from degree of freedom for all three of them, and then you calculate K for one molecule. Okay, K for one molecule, and then you calculate K for n molecule. For all three cases in your table. So satu table kamu buat yang panjang punya, bermula daripada degree of freedom, cara pengiraan kinetic energy untuk satu molekul, cara pengiraan kinetic energy untuk n molecule. Alright, so 5 minutes for you to complete it now. Okay, sendiri keluarkan kertas atau dalam buku Anda buat satu jadual ringkas to show you the difference. Okay, the table given in your books is the table without rotational motion, so it is incomplete. So try to complete it. Coba buat jadual sendiri supaya Anda paham. So catat, coba siapkan dia. Tunggu kawan kamu balik dari tandas, kita akan sambung. Alright, now let's look at exercise 4. Okay, exercise 4 is just a very short and simple exercise. So if you look at questions 1, estimate the average mechanical energy. Now, when it comes to mechanical energy in your syllabus, actually it refers to both kinetic and the potential energy. And according to assumptions, we know that the potential energy in this case is equals to 0. Therefore, when question says mechanical energy, means that it's talking about the kinetic energy. So calculate the average kinetic energy possessed by a molecule in CO2 gas at 300 Kelvin. CO2. CO2 belongs to which types of atoms? Atomic. CO2 is diatomic. It is polyatomic, all right? So you yourself have to know what types of atomic it is. Okay, so questions will just tell you maybe you have a H2, you have a CO2, or maybe you have a helium atoms, and oxygen atoms, and so on. You yourself have to know whether it belongs to monoatomic, diatomic, or polyatomic. So obviously, for questions 1, CO2, we know that it is polyatomic. Okay, so CO2, it is polyatomic. Now, why is it so important to know whether it is a poly, di, or mono? What is the information that we can get from a terms polyatomic? Degree of freedoms. So what happens to the degree of freedom? What is the degree of freedom? 6, okay? Because now you want to calculate average kinetic energy, means that you want to calculate the total of the translational and also rotational kinetic energy. Therefore, we use total degree of freedom. So degree of freedom for polyatomic is equals to 6. Okay, and then now it tells you your temperature T is equals to 300 Kelvin. And then we know that the general equations for average kinetic energy, okay, average K is equals to F over 2 and KT, right? So F we have it already, which is equals to 6. And then K is the Boltzmann constant. And temperature given 300 K. Now the questions would be, what is the values of N? You look at the questions. Questions mentions a molecule. So which means N is equals to 1. Good. So n is now equals to 1 because questions say a molecule. Okay, so 1 molecule. So now that you have all of the information, you just plug it in and eventually you will obtain 1.24 times 10 to the power of negative 20 joule. Right? So questions 2 is exactly same as questions 1. I will leave it to you. So I give you 3 minutes to solve questions 2 by yourself. You just have to know helium belongs to which type of atomic and N2 is which type of atomic. So helium is a mono, poly or di? Helium. It is monoatomic. Then how about N2? Diatomic. Good. All right. So you know the types of atomic already. Now you can solve questions 2. Exactly same as questions 1. Right? You just test whether you understand what types of atomic it is. So 3 minutes for you to solve questions 1 and 2. Just a very short and simple questions. Okay, 1 more minute. All right. So now let's look at questions number 3. Question number 3, a vessel contains hydrogen gas of 7.5 times 10 to the power of 17 molecules per unit volume. Now, this is a very tricky part, okay? Because the value given, it doesn't belong to any single variables. It belongs to what now? You look at the phrase again, okay, the statement again. 7.5 times 10 to the power of 17 molecules per unit volume, which means this value is actually N over V. Okay, it is not N, it is not V, but it is N over V. So given N over V equals to 7.5 times 10 to the power 17 molecules per meter cube, okay, per unit volume per meter cube. And the root mean square speed, which is your VRMS given, is equals to 2.5 times 10 to the power of 3 meter per second at temperature 30 degrees C. Now, T is 30 degrees C, but then we know 30 degrees C is not SI unit, so it is equals to 303.15 Kelvin. Okay, 303.15. So given molar mass of hydrogen gas, so you are given M is equals to 2 gram per mole. Now, once again, you are given the quantity in gram per mole, the unit in terms of gram per mole. So we need to change it into kg. So 2 times 10 to the power of negative 3 kg mole negative 1. Right? Kg mole negative 1. So given molar mass of hydrogen is 2 gram per mole. Number of Avogadro, as usual, 6.02 times 10 to the power of 33 mole negative 1. And Boltzmann constant K is equals to 1.38 times 10 to the power of negative 23 joule per Kelvin. Questions A, calculate the average translational kinetic energy. So now question is asking for translational kinetic energy, not average kinetic energy, not rotational energy. So even though hydrogen gas, your H2 is a diatomic, but it doesn't matter. Why? Because now the things that you're looking at is just translational motion. So when it comes to translational motion, okay, the F is equals to 3, right? So translational kinetic energy, so again, our general equations, KTR is equals to F over 2 NKT. So what is the values of N? 1, okay, once again, because the question says a molecule, okay, so N is equals to 1. So we have F equals to 3, N equals to 1, and then given temperature is 303.15, you should be able to determine the values, the numbers of translational kinetic energy. Okay, so questions A is just very simple, very straightforward questions. Questions B. Questions B asks you to calculate pressure. Okay, but then you cannot use PV equals to nRT. Why? Because you don't have enough information. You don't have the volume, so you cannot use it. Okay, you don't have you don't have volume. What you have is the molecules per volume. So let us try the other equation. Okay, which is PV equals to 1 over 3 and then mean square speed. All right, so this is another equation that can be used to determine pressure other than PV and RT. Okay, so PV equals to 1 over 3 NmV squared. Now the reason why I choose this equation is because if I rearrange the equations, I move this V to the other side, then I will obtain P is equals to 1 over 3 N over V. So this is the values given. So N over V and then mV squared. Right? So if I rearrange the equations, then I can obtain a value like this. But now I have another question. I don't have the mass, right? So I don't have the mass. So what should I do with these equations? So now again, I know that N is equals to M over M, and this equals to N over NA. Now, when it comes to this equation, one thing that you need to take note, once again, the M in this equation is for one molecule, right? The M in this equation is the mass of one molecule. So now let us try to crop this part out and try to determine the values of the mass, right? So can we calculate the values of the mass? So I'm going to rearrange the equations. Okay, I'm going to rearrange the equations. So since you're looking at just one molecule, okay, because this m, the m in this equation, PV equals to 1 over 3 mmv squared. This m is just for one molecule. Therefore, my m is equals to 1. So if I rearrange the equations, I will obtain an equation m is equals to molar mass divided by number of Avogadro. Now I can use it. Why? Because I have molar mass right here, and that number of Avogadro is just a constant, right? So the n here is equals to 1 because according to the question, this mass is the mass for just one molecule, all right? For just one molecule. So this m, I'm going to remove it, and then I'm going to replace it with molar mass divided by number of Avogadro. So you can then obtain the values of the pressure, okay, which is equals to 5.19 times 10 to the power of negative 3 Pascal. Okay. So this question is a bit difficult because it combines a few equations into one equation. So this is what we call hot question. Okay, it is very hot. Why? Because you need two additional equations to solve these questions. So if you can understand this question, it means you got a very good concept already. So remember, take note, the m is the mass of one molecule. Okay. So the only times where we use total mass in our equation is when you calculate the number of mole. Alright, so kalau kamu nak kira number of mole, ini kena guna total mass. Tapi kalau kamu nak kira dalam equations untuk VRMS, untuk pressure, all these m, they are the mass of just one molecule. Okay, just one molecule. Bagi kamu sikit masa untuk faham dan buat catatan sebelum kita bergerak ke soalan terakhir. Okay, so far so good. Right, bagus. So now let us look at last questions. Okay, let us finish off with today's class. So a vessel contains an ideal diatomic gas. Okay, so it tells you it is a diatomic gas of a 20 degrees C. So now you have a temperature at 20 degrees C, and the total translational kinetic energy of the gas molecule is 3 times 10 to the power of negative 6 joule. The mass of the gas is then double. So if you look at this type of question, it means that now you have two different situations. So you should have two set of value. All right, so set 1 and then set 2. So what happens in set 1? Now it tells you you have an ideal gas at temperature 20 degrees C. So now I have T1 equals to 20 degrees C, which is equals to 293.15 Kelvin. Okay, and then the translational kinetic energy. Okay, translational kinetic energy. So KTR1 is equals to 3 times 10 to the power of negative 6 joule. And then the mass of the gas is then double, which means initially you have the mass which is equals to M1. Okay? So now it tells you, oops, this is 2. So now it tells you the mass is then double. So which means your M2 is now equals to what? Very good, 2M1. Okay, 2M1. And then the total translational kinetic energy has now becomes, okay, so your KTR is now equals to 9 times 10 to the power of negative 6 joule. Okay, 9 times 10 to the power of negative 6 joule. So determines the new temperature of the gas. So you want to find out what is the values of T2. So when you have a questions like this, the things that you can do is try to identify what is the equations that can be used first. When you have two sets of information, it means that you can form two equations. Your first task is to find out which equations can be used. So now let's see. Well, now I have translational kinetic energy. Translational kinetic energy degree of freedom is always equals to 3. So KTR is now equals to 3 over 2 NKT. Okay, 3 over 2 NKT. So the things that I can do right now, well, if I look at these equations, I cannot relate it to mass. Okay, I need to link these equations to mass. So what can I do is, okay, now I want to rearrange the equations. I'm going to change it first into 3 over 2 nRT. So KTR at the same time is equals to 3 over 2 nRT. Okay, because PV equals to NKT equals to nRT. So translational kinetic energy can also be written as nRT. Now, can I simplify the equations? I need mass. So what can I do right now is, now I have mole. I want to relate it to mass, right? So therefore, M is equals to M over N. So initially, this equation, okay, this equation, you cannot use it. If you want to use it, it becomes quite complicated. Why? Because if you use M over M equals to N over NA, then in your calculations, you need to keep the number of Avogadro some more. But if you change it into nRT, then what you have to do is just M over M. Right? So it's up to you whether you want to use a first set or you want to use a second set. Terpulang pada Anda. I give you choices. Okay, you yourself decide which one to use. So I would prefer the second one because the equations will become more simple. So I sum it into the equation. I then have KTR equals to 3 over 2 M over M RT. Okay, so I can form two equations based on these equations. Okay, this general equation. But then I have one more question. If you look at this equation, these equations, well, it needs KTR. I have it in my equations here, in my information table. I need a mass. Do I have the information about the mass? Yes, I do. Okay, I have the mass. The mass is being mentioned in the questions. Okay, I have the temperature here. That is fine. R is just a constant value. But now how about M? What should I do with this molar mass? Why? You say it's the same why. Because you're looking at same gas. Very good. Okay, because now you're still using same gas. You're not changing the type of the gas, which means both of them, they are going to have same molar mass. Okay, they are going to have same molar mass. So what you need to do right now, you form an equation by using the information from set 1. You form another equation by using the information from set 2, and then you do simultaneous equation to determine the values for T2. Alright, so do it now. Once you get the values, then that's all for today. Okay, sekarang saya bagi kamu sedikit masa untuk praktis Anda punya matematik. So buat dua equations, buat persamaan serentak. Alright? Okay, so online punya saya stop recording dulu.